How do we make sodium amide? And what is it? Why is it important? So we take some, what's the name of this compound? Ammonia and sodium metal and a little iron 3 salt act as a catalyst. And if we wanted, this is the reaction that occurs. So when I think about acid-base chemistry and how do we get these powerful bases at some point in time, or powerful acids, and we think about acid-base reactions, we always form the weaker acid and weaker base. So how do we get to sometimes a powerful acid or base? And redox chemistry is sometimes the answer. So we have sodium metal has an oxidation of 0. It really wants to give up some electrons, and it gives enough electrons to this that we get some hydrogen gas, and we get this interesting species here. Reminds me of calculating formal charge at the beginning of the semester. Nitrogen likes to form 3 bonds. Here it only has 2, has a full valence shell of electrons, so nature's good that way, and it's going to have this negative charge. So what good is a sodium amide? Well, here we have an alkyne. It's a terminal alkyne because hydrogen's on the triple bonds at the end. And if we hit it with this reagent, this is a strong base, pulls off that proton. Sodium's still hanging out as a counter ion. And so when I look at this, I see an acid and I see a base. So this thing over here must be what? Nobody didn't shout it out at once. So we can go all the way back to the beginning of the semester. Ammonia, you put it in water, it makes ammonium hydroxide, classic Arrhenius base. Here we're calling it an acid. Why are we calling it acid? Because we get to do that in organic chemistry. Acyl group. So we might even say we formed some sodium acetylide. So what's the product to this reaction? You're saying, oh man, we've got into this chapter. I don't know, an alcohol, alkene. Any of you thinking those thoughts in your head? Good. I'm glad, because let's draw what we get. So, of course, this is a good review of acid-base chemistry. It also gives you organic chemistry knowledge in that these type of reactions have to be done under anhydrous conditions. What does that mean? Yeah, you got to make sure everything's dry, because if there's some water, this acid-base chemistry occurs and kills your species you want to do some chemistry with. So terminal alkynes are more acidic than other hydrocarbons due to the higher S character of the sp hybridized carbon, and terminal alkynes can be deprotonated quantitatively. That means all the way to the product side of the reaction with sodium amide. Hydroxide and alkoxide bases are not strong enough to deprotonate the alkane. Guess I just erased it. I don't know why I did that. So here's a typical pKa for an terminal alkyne, that acidic proton. Here's our sodium amide. So this thing has 4 carbons. We got but1-ine. So this thing would be named sodium butine. Here's the pKa of ammonia. Here's the pKa. So we always want to form the weaker acid and the weaker base. So we look at ammonia and say pKa of 36. That's a larger number than this pKa of 25. So this acid-base equilibria will push everything over here. And we use this reagent to form this reactive species. And it says here the acetylide ion is a strong nucleophile, also a very strong base, as we just saw, that can easily do addition and substitution reactions. Addition. Haven't seen one of these yet. Well, actually, excuse me. We've seen all kinds of addition reaction to alkenes, electrophile to alkenes. But you're going to see something a little different. Reminds me of that Alex assignment where you had all these different types of reactions. It was at the beginning of the semester, and one of you said it was difficult. And I remember I actually did a bunch of those, and I thought, man, and I go, well, it's really good because addition, you see two reactants in one product. They come together, kind of follow the words. So this is a very good setup for an SN2 reaction. We have the most reactive alkyl halide out there, right? The methyl. Can the methyl undergo an elimination reaction? No, what are you going to form a double bond to? There's only one carbon. I'm waxing ridiculous. All right, so slams in that carbon, iodide leaves, and there you've increased the carbon chain. So this is one of the best methods for synthesizing substituted alkynes as a nucleophilic attack by the acetylide ion on an unhindered alkyl halide. SN2 reactions with primary alkyl halides lengthens the alkyl chain. Unhindered alkyl halides work better in an SN2 reaction. That's why the methyl is better. So what else do strong bases do? Elimination reactions can occur. So notice this thing here, we say to ourselves, oh, let me make this branched alkyl group, attach it here, and we don't see our substitution occurring. So if the SN2 reaction is not possible, then elimination will occur. So here's a typical draw the reaction product, and we got three things going on. So what is this reagent going to do? Absolutely, it's going to take off this H, it's going to deprotonate it, and here's our nucleophile. Now I drew something crazy here. Looks like an aldehyde. Looks like 1, 2, 3, 4, 5, 6. I don't know why I made it so long. I don't like drawing all these. So this carbon and this oxygen, we have a electronegative element and a not so electronegative element. So that produces a partial positive charge on carbon and a partial negative charge on oxygen. So this thing can slam into there. Those electrons jump up. So now we have something that looks like this. And then we add hydronium ion, which is going to protonate that. Forgot a hydrogen. Forgot that hydrogen right there. Do as I say, not as I do. So we've made this alcohol. Any questions? So we want to start seeing some longer synthesis like this. Now that you got a lot under your belt, what do you have under your belt? How to make an alkyl halide from an alkane with halogenation. UV light, heat, addition to a double bond. You can make lots of alkyl halides. What you can do with the alkyl halides, substitutions. And now you have, here's the addition. We say an acetylide, an alkyl acetylide ion will add to a carbonyl carbon, and we'll see that we get either secondary alcohols or tertiary alcohols, whether we use an aldehyde or a ketone. Any questions? I think we're going to end here today. We have a big long lab.